example that we demonstrate in our hands-on module is image classification, and that's probably the most common category of image analysis problem that we address with deep learning techniques. And what that translates to is being able to classify an image either in our demonstration as a chest radiograph or an abdominal radiograph, but also you can classify for the presence of specific pathologic findings on a chest x-ray, such as pneumonia in one of the prior RSNA challenges. But some other methods that you can use that actually require significantly less data in certain cases include object detection, where you train a model to draw a bounding box around an area of interest in an image, such as an opacity on a chest radiograph or hemorrhage on a brain CT, and then classify that section of the image accordingly, either as hemorrhage or calcification perhaps, or as pneumonia or as some other opacity like a lung nodule. Then there's also image segmentation. So that's where you're actually training a model to highlight the areas of an image that are of interest to you. So potentially segmenting out relevant anatomy, such as the basal ganglia on a brain CT or brain MRI. And then finally, there's another approach to using deep learning for image analysis, and this is more in sort of the pre-processing and post-processing of images, and that's deep learning reconstruction. And that can consist of super resolution, which is where images of lower quality are then transformed by a network to be of higher quality, or denoising, where an image that's got a lot of noise in it, such as a low-dose chest CT, can be denoised, or some of that noise can be taken out by a neural network. And those are the major applications that we're seeing deep learning used for in image analysis today. The key takeaway is really understanding which of your subsets are exposed to the model and how they're exposed to the model. So the training data set is directly exposed to the model during training. It is what the model is using to update its weights or parameters and try to formulate that prediction. In our case, from the hands-on module that we did, we're talking about trying to update the parameters to be able to detect differences between chest radiographs and abdominal radiographs. The validation data, on the other hand, is indirectly exposed to the model during training. You use it to update some of the parameters about your training and decide when to stop training. But over multiple experiments, there's a concept called data leakage, where some of that information from the validation data set can actually get built into the model through multiple repeated exposures during validation and experimentation while training a model. But really what's important to understand model performance at the end of it all, at the end of your training, is to hold out the test data set and make sure that your model never gets exposed to it. To be able to get a better sense of what the real world performance is likely to be. And it's even better if that test data set can be more representative of the type of data that you expect to exist in the real world. Data from a variety of different geographic locations, from a variety of different patients of different demographics, and from a variety of different scanner models and scanner types. But the most important concept here is that you want to keep your test data set completely separate from your training and validation data sets to avoid leakage of your test data into the model's parameters and weights. Perhaps the most important thing is that the technique allows you to train a better model with less data and less computational resources by leveraging someone else's pre-training on a larger data set. And there are economic and environmental benefits to this as well. labeling data takes time, and radiologist time in particular is very valuable. That's time spent labeling data for an AI model is time that they're not spending taking care of patients. And so we want to be judicious in our utilization of that resource, the radiologist time. But also in terms of computational resources, the type of computation we need for these models requires different types of accelerated high performance computing, but most commonly we utilize a graphics processing unit or a GPU. And this compute is not cheap and it expends a lot of energy. The carbon footprint of training a large model can be on the orders of the cumulative lifetime emissions from multiple gas-powered cars. So the less time we can spend training the model, the less computational resources we need to train the model, the better it is for our economic bottom line, and the better it is for the environment and our carbon footprint from creating AI. And this is a concept that's been brought up in recent years, and there's increasing awareness in the AI and machine learning community more broadly. I think probably less so in the radiology community at this point in time, but I think more and more people are becoming aware of this. And transfer learning is an important technique for reducing the amount of time, the amount of computational resources, and the amount of data that you need to train a high-performing AI model.